Okay, let's see. Can everyone hear me out there?
Yes.
Yep.
Okay, thanks. All right, welcome back to our last hybrid week, last full hybrid week. All right, so today what we're going to do is we'll finish up the section on difference equations, and we'll study the predator-prey model, and then we'll sort of move into the notion of orthogonality, and then that will sort of take us towards the end of the semester. All right, so let me review the idea of difference equations. So basically, you have the following. So A, let's say, is an m by n matrix. And the difference equation is given by a matrix equation in the form UK plus 1. Sorry. So UK plus 1 is A times UK. All right. And with an initial value condition U0. All right, so you have this system where the next step is given by multiplying UK, a vector UK, by A. Right? Now, what we saw once we did this was that UK is going to be A to the K times U0. All right, so this is a consequence of the difference equation. Now, we want to take powers of A to the K. And so if we want to take powers of A to the K, then it's very useful if the matrix that we have on hand is diagonalizable. So suppose we're in a nice case that A is diagonalizable. Okay, so suppose A is diagonalizable. So what does that mean? It means that A is equal to SD S inverse, where D is of the form lambda 1 up to lambda n. Okay, so the lambda i's are eigenvalues of A. And then we have corresponding eigenvectors, which are down the columns of S. So S is going to look like x1 up to xn, where the xj's are eigenvectors of A. Okay, and x1 is eigenvector with eigenvalue lambda 1. X2 is an eigenvector with eigenvalue lambda 2, et cetera, et cetera, et cetera. Okay? And now what we can do is we could formulate S inverse U0, and we could just multiply the inverse times U0, and then we get another vector C1 up to Cn. Okay? So then once we have this set up, we saw that the solution of the difference equation can be expressed in terms of x, the ci's, and the lambdas. And the lambdas we take to certain powers. So then the conclusion is that UK is equal to C1 lambda 1 to the K times x1 plus C2 lambda 2 to the K times x2 plus Cn lambda n to the K times xn. Okay. All right, so that gives us a solution of the difference equation relative to the eigenvectors and the eigenvalues. Okay, so one thing nice was we were able to solve and find a closed formula for the Fibonacci series. So let me give you the example. I'm not going to redo everything, obviously. So okay, so for the Fibonacci series, we had Fk was equal to 1 over square root of 5 times 1 plus square root of 5 over 2. So this is the golden ratio to the k minus 1 minus the square root of 5 over 2 to the k. So this Fk is the kth Fibonacci number. Okay. All right, any questions on this? So this Fk was obtained by just using the formula, figuring out what the eigenvalues are and the eigenvectors. Questions? Okay. All right, so now let's move on to another example. This is going to involve multinational companies. And what we can do is we can have this, we can sort of look at a yearly type of behavior. So after a certain amount of time, like a year, assets get traded among companies. And then we can look at what happens in the long term in terms of whether there's a stable solution or an unstable solution. All right, so let me give you an example. Okay, so suppose multinational companies in the US, Germany, and Japan have assets of $4 trillion. Okay, so in the entire system, there's 4 trillion. And this 4 trillion is going to move around in various ways. Okay? So at the start, we have 2 trillion is in the US, 2 trillion is in Germany, and 0 is in Japan. Okay? All right, so that's kind of the initial value condition. So we'll actually write that out in a second. All right, so each year, 1/2 in the US stays. Okay, so 1/2 of the US amount stays in the US. 1/4 goes to Japan, and 1/4 goes to Germany. Okay. For Japan and Germany, 1/2 stays. So 1/2 stays in Japan, 1/2 of the amount Japan has in assets stays, 1/2 of the amount Germany has stays. And then for each one, 1/2 is sent to the US. Okay. All right, so the goal is find out what happens as we go to infinity. So find what we call the stable state. What we call it? Yeah, the steady state. i.e. when k goes to infinity. Okay, so what we have is we have this difference. We have this system where we can actually set it up in terms of a difference equation. So let me do some labeling. So US will mean the United States, and J will stand for Japan, the amount that we have in Japan, and G will stand for the amount we have in year K in Germany. Okay? So first of all, the initial state, so let's see, let's do US at 0, Japan at 0, and Germany at 0. Okay, so let's go back up here. So at the start, there's 2 trillion in the US, 2 trillion in Germany, and 0 in Japan. So that's 2, 0, 2. Okay, everyone all right with that? All right, now, so in the K+1 year, let's write this in terms of the kth year, okay? So we know that 1/2 of the amount in the kth year stays in the K+1 year, right? And the US receives what? It receives 1/2 of the amount from Japan and 1/2 of the amount from Germany. Okay, is everyone clear on that? From the information? Okay. So let's see what happens with Japan in the K+1 year. Well, how much does it get from the US? So it gets 1/4 from the US amount from the previous year. How much does it get from its own? Well, 1/2 stays. And it gets nothing from Germany. Okay? And similarly for Germany in the K+1 year, how much does it get from the US? It gets 1/4. It gets nothing from Japan. And it keeps 1/2 of its own. All right, is everyone clear how we use the data to get these equations? All right. So now if I set UK to be equal to, that's a UK+1, to be these amounts, US K+1, J K+1, and Germany at the K+1 stage, okay? Well, what matrix do we get? Well, the coefficients are just the coefficients in these equations, right? So it's 1/2, 1/2, 1/2, 1/4, 1/2, 0, and 1/4, 0, 1/2 of the amount in the kth year, UK. All right, so good. This is a difference equation, and this is A. Okay. So can I find UK? Yes or no? What should I be thinking about trying to do?
Diagonalize the matrix.
Right, so we want to actually diagonalize it, see if this matrix is diagonalizable. So I'm going to give you the data after you do the computation. So we're not going to do the computations exactly, but I'll give you the information. Okay, so the idea is diagonalize A. Okay, all right, so the eigenvalues of A are lambda 1 equals 1, lambda 2 equals 1/2, and lambda 3 equals 0. Okay, so we've done enough examples. You take a minus lambda I, you look at its determinant, you find the roots of the characteristic polynomial, et cetera, et cetera. And that's how you find these, okay? And then you can find various eigenvalue vectors. So with corresponding eigenvectors, and I'll just label them x1 is equal to 2, 1, 1. x2 is going to be equal to 0, minus 1, 1. And x3 is equal to 2, minus 1, minus 1. Okay, so you find the eigenvectors by looking at the null space of A minus lambda I. Okay, we've done that lots of times. All right. So now what's the matrix S? So the matrix S, we just have the eigenvectors down the columns. Okay. And then you can find S inverse by various methods. So either you can use cofactor method or you can use Gaussian elimination. So then you can find S inverse, and let me write out the answer for the inverse: 1/4, 1/4, 1/4, 0, minus 1/2, 1/2, and 1/4, minus 1/4, minus 1/4. Okay? And then you take C, which is S inverse U0. So I'll just write that out. 1/4, 1/4, 1/4, 0, minus 1/2, 1/2, 1/4, minus 1/4, 1/4. And the initial value condition, we go way back up here, is 2, 0, 2. Okay? And then you matrix multiply. So if I take the dot product of 2, 0, 2 with the first row, I get a 1/2 plus 1/2, that's 1. The second one is going to be equal to 1 also. And then the last one is 0. I have a negative? It's a negative here. Sorry, there's a negative here, so it's 0. Okay. Questions on this part so far? So you find the eigenvalues of A, you find the corresponding eigenvectors or find corresponding eigenvectors. You put them in the matrix S. You could find S inverse by various means, and then you get the vector C. So now we have all of the data necessary to apply this formula up here to find UK. All right? So let's do that. So therefore, everything's nice and neat. UK is equal to C1 lambda 1 to the K x1 plus C2 lambda 2 to the K x2 plus C3 lambda 3 to the K x3. Okay? So remember what lambda 1, lambda 2, and lambda 3 are. So it's 1, 1/2, and 0. So for the first one, and what is C1? C1 is 1. So let me just write this out. I get 1, 1, and the first vector is 2, 1, 1. C2 is 1. The second eigenvalue is 1/2. And x2 is going to be equal to 0, minus 1, 1. And then I get 0 for the third eigenvalue. So I don't have anything else. Okay, so let me clean this up a little bit. So this is 2, 1, 1 plus 1/2 to the K times 0 minus 1, 1. Okay? So we found a solution, or the solution for this difference equation. All right, now what happens as k goes to infinity? What happens? What does the solution tend to?
0 or 2, 1, 1.
1, 1, okay? Because 1/2 to the k goes to 0, right? So that means that UK tends to 2, 1, 1. All right? So eventually this sort of, sort of dynamic system or sort of difference equation system, which is sort of a dynamical system, eventually is going to stabilize. So 2 million or 2 trillion will be in the US, 1 trillion will be in Japan, and eventually 1 trillion will be in Germany. Okay. Any questions on this? All right. So, so let me give you some terminology, since we did this example. So the difference equation is called stable, okay, if all the eigenvalues satisfy that the absolute value of the eigenvalue is less than 1. Okay. It's neutrally stable if some eigenvalue is equal to 1 and the rest are strictly less than 1. Okay, so you're allowed to have one of the eigenvalues in absolute value be 1. Okay? And it's unstable if at least one eigenvalue has absolute value strictly bigger than 1. All right, so if we go back to here, the last example, we have 1, 1/2, and 0. Okay, so this is an example of something which is neutrally stable. Okay. Okay, any questions on this? All right, so now let's apply this to another example. And this is an example which I think is in your book, or some examples that you'll be doing in your book. And this is the predator-prey systems. All right. So what I'll do is I'll give you an example of a predator-prey system. A lot of them sort of work the same way as what we've done in the past. They satisfy some difference equation, like the one that we did in the previous example. And then once we have it in the difference equation, we can just apply the exact same techniques that we had before, involving eigenvalues and eigenvectors, to solve the difference equation and then sort of analyze what happens in the limit. Okay. All right. So the example I'd like to focus on is owls and rats. Okay. All right, so owls are the predator and rats are the prey. And as you know, if we don't have the predators around, the rat population will just continue to grow and grow and grow. So it's really good to have predators in this instance. All right, so let's let at the kth year, we have O sub k and we have R sub k. So O of k is equal to the number of owls in, let's say, year k, and R of k is the number of rats in year k. All right. Now, let me give you some data. So, people go out into the field and then they sort of figure out, how many rats and how many owls live after a certain amount of time. Okay. So in the K plus first year, you have 0.5 number of owls that remain, and then the number is 0.4 times the number of rats. Okay. And the number of rats in year K plus 1, well, we're going to put in this constant O sub P minus P times O sub K times 1.1 times the number of rats. All right, so this is the difference equation. And in this problem, I'm not going to specify an initial value. We're going to let the initial value kind of vary. All right, so we're just going to work with the difference equation for now. Okay. All right, so let's make some observations. So if you look at these equations, now if R of k is equal to 0, all right, so suppose we don't have any rats in year k, then the owls are going to decline. So then O sub k plus 1 is going to be equal to 0.5 O sub k. All right, so without any food, the owls are going to start to diminish in population. Okay. All right, so this minus P times O sub k, this measures the death rate of rats due to owls eating rats. Okay, so we have this measure inside of here, and we could tweak the p. We could sort of make p different values. Okay, so the third thing to observe is in the second equation, if there are no owls, so then R of k plus 1 is going to be equal to 1.1 times R of k. So the rat population grows. Which may or may not be such a great thing. Okay. All right, so we have this difference equation. So we have UK plus 1, and I'll just put the numbers in, 0.5, 0.4, minus P, and 1.1. Actually, I don't need the parentheses here, so let me just get rid of the parentheses. Okay. All right, so we have this, and then we have u to the k. All right, now let's specify p for this problem. So suppose in this problem, p equals 0.125. Okay, so now our a is going to be equal to 0.5, 0.4, -125, and 1.1. All right. Okay, so in order to solve this, we want to see if it's diagonalizable, right? So we want to determine, so we would like to diagonalize A. All right, so how do we diagonalize A? What do we need to do? Anyone? How do we always diagonalize A? What do we need to find? What did we do in the last problem?
Well, we found a similar matrix.
Right, so how do we find the similar matrix? What information do we need?
Eigenvalues.
Right, we need to find the eigenvalues, right? Okay, so to find the eigenvalues, we have to write out the characteristic polynomial. So let's do that in this case. So the determinant of A minus lambda I. So that's 0.5 minus lambda, 0.4 minus 0.125, and 1.1 minus lambda. Okay. So when you write all this out, I'll just write out certain steps. So I get 0.5 minus lambda times 1.1 minus lambda, and then the product of this turns out to be plus 0.05. Okay, so AD minus BC, right? Okay, so you do all this simplification, and eventually you get lambda squared minus 1.6 lambda plus 0.6. Okay. All right, so then you use a quadratic formula. So lambda is equal to minus b, so it's 1.6 plus or minus the square root of b squared. 1.6 squared minus 4, 1 times 0.6, all over 2. Okay. All right, so then you do some arithmetic, and this is 1.6 plus or minus 0.16 over 2. And so I get 1 or 1.2 over 2. So the eigenvalues are 1 or 0.6. Okay? So these are the eigenvalues. Yeah, I skipped a few steps, but a lot of those steps are just purely, you know, like addition and subtraction and that sort of thing. Just, you know, basic arithmetic, right? All right, any questions up until this point? All right, now what other information do we need to solve the difference equation?
We need S.
Right, we need the S, okay? So next thing is we're going to find the S, which are the corresponding eigenvectors, okay? All right, so if you do that for A minus 1 times lambda, you get the matrix minus 0.5, 0.4, minus 0.125, and 0.1. And then you can check that an eigenvector for this is 4, 5. Okay, so if you take 4 or 5 times this matrix up top, you get 0. Okay, and then when you take A minus 0.6 times lambda, you get the following thing. You get minus 0.1, 0.4, minus 125, and 0.5 here, right? Okay, because you're subtracting off 0.6 from the diagonal on both of those, okay? And your eigenvector here, when you do Gaussian elimination, you get 4, 1. Okay? So your S is going to be 4, 5, 4, 1. Okay? All right, any questions up until this point? All right. Now, so one other thing we should kind of observe is we had this equation up here. So remember that the C here is going to be equal to S inverse times U0. So we can actually solve for U0 by multiplying S on both sides. So let me go down here and do that, okay? So let's take a little time. So we have that C1, C2 is S inverse times U0. Now, I didn't specify what U0 was. So that means that U0 is equal to S times C1 and C2. Now, we know what S is. So this is a vector x1 and x2. And so we can write U0 as C1 times the vector x1 plus C2 times the vector x2. Okay? So we could take this equation that we had before and just re-express U0 in terms of the C's and the columns of the matrix S, the eigenvectors. Okay. Good. All right. So the solution for our difference equation, is, well, we have U of k. This is C1 lambda 1 to the k times x1 plus C2 lambda to the k times x2. Okay, this is just exactly the equation that we've been using for, the last example and for the Fibonacci series. So let's plug things in. So what do we get? We get UK is going to be equal to C1 1 to the k, okay, times 4, 5, plus C2 0.6 to the k, and then 4, 1. Okay, I'm just plugging in the eigenvalues and the eigenvectors. Right? So as k goes to infinity, the limit as k goes to infinity of UK, well, what does that become? Well, minus 0.6 to the k, that goes to 0, right? So this is exactly like the problem we had before with the multinational companies. So this term here is going to tend to go to 0. And then 1 to the k tends to 1. So I just get what? So what's the answer here? Anyone?
C1,
4, 5.
C1 times 4, 5. Okay, so the answer depends on the initial value condition. All right. Okay, so if C1 is not 0, then the owl and rat population will stabilize in size. Okay, and of course, it's dependent on what the initial value condition C1 gives you. All right. And let's say C1 is 1, so you'll end up with 4 and 5 rats left. Okay, 4 owls and 5 rats. And now, if you notice, if I change, oops, what's this? Not quite zoomed on me, but anyway. So if I perturb the P, okay, so if I change this P up here to some other value, then it's going to change the this dynamical system. Okay? So if P is perturbed, then the eigenvalues can definitely change. And also the stable solution. Okay, any questions on this so far? Yes, no? All right, so in the remaining time, I'd like to start in on inner products. You've seen some of this before when we did matrix multiplication. And so we'll just sort of start in with the basics on inner products. And then on Wednesday, we'll look at the properties of inner products further, and then talk about like orthogonal matrices. Okay. All right. So the next topic will be on inner products, length, and the notion of orthogonality. Okay. All right, so basically the idea of the inner product is just the dot product. So we've seen this before. So if you take the dot product of two vectors, so we have V and W and Rn. So the idea we saw before was if you take V dot W, we express this as matrix multiplication, V transpose times W. So let me just write that out. That's V1, V2, let's say Vn as a row vector. And then this is a column vector, as always. And the answer was V1, W1, V2, W2, plus Vn, Wn. Okay, so what we do is we take the product of the corresponding components and then we sum them up. Okay. All right, so what are the properties of the dot product? So these properties are sort of come from like the matrix multiplication properties. So it turns out when I take the dot product of V and W, it's the same as the dot product of W and V. Okay, so you can see this from the formula. If I interchange the V's and the W's, I get the same answer. Okay. The second property is that if I take two vectors U and V and I dot it with W, this is like the distributive law. So this is U times W plus V times W. Okay. Dot products behave well with respect to scalar multiplication. So if I take a scalar multiple on V on W, I can basically move the scalar anywhere I want. So this is C times V of W. Okay. And finally, an important property is that if I take the dot product of a vector U with itself, this is always bigger than or equal to 0. Because when I look at the formula, I'll get, if U, the V and W are the same, namely they're U, then I'll get U1 squared plus U2 squared up to UN squared. Okay. Let me just write that out. So U with U is equal to U1 squared plus U2 squared plus UN squared. Okay, so clearly it's going to be bigger than or equal to 0, right? And the dot product of U with itself is equal to 0 if and only if the vector U is equal to 0. Okay, the sum of squares is equal to 0 if and only if all the components are equal to 0. Okay, any questions on this? Okay, so the final sort of concept of the day is the length of a vector V, which will denote with respect to these this absolute value. And it's just the square of the lengths of the components. Okay, so the idea is that if I have a vector here, V1 and V2, you know, if you just use the distance formula, the length of V will just be the length of the vector from the origin to the tip, when you think of the vector as a point in Euclidean space. Okay, so the length is equal to the sum of squares. Okay, let me stop here and ask if there are any questions. Yes, no? All right, so we'll stop here and then we'll continue on Wednesday with more about dot products and orthogonal matrices. Okay.
Thank you.
Welcome.
Hello.
Hello.
Bring up my text.
Okay, hold on for a second.